quickly want to just tell you about Sahoma Controlware and how incredibly grateful I am to, during this pandemic, have an opportunity to begin a partnership with Justin Dean and his family and Sahoma Controlware. Just a little bit about the business in case anybody doesn't know. It's been in business since 2013. Deep experience in automation systems with critical control, DCS, heavy industries, sill safety, motion controls. What's up, guys? I'm Sean Terrell, the senior project engineer at Sahoma Controlware in Edmond, Oklahoma, and I'm going to be putting together a tutorial for you about something that I've been facing as a development solution problem or a development problem with our own infrastructure and some of the things we've been working on and putting together. And that's a way to kind of create an extensible, adaptable data generator that can essentially represent some kind of a field implementation, give us live data that is realistic and moving values in analog and different realms, and give us some decent visual feedback of how the data will be represented in different dashboards, different implementations, different visual compilations that we're doing. So I'll get into that in just a minute. First, I really quickly want to just tell you about Sahoma Controlware and how incredibly grateful I am to, during this pandemic, have an opportunity to begin a partnership with Justin Dean and his family and Sahoma Controlware. Just a little bit about the business in case anybody doesn't know. It's been in business since 2013. Deep experience in automation systems with critical control, DCS, heavy industries, sill safety, motion controls. Both Justin and I come from a little bit different background than a lot of folks in the automation industry. His early career was spent at Johnson Space Center in Houston, working for NASA, doing different control simulations for NASA for any purposes they had as far as for the astronauts. And I came through the Navy and started as a contractor for the Naval Undersea Warfare Center, doing Unix and Linux-based weapons control system testing, evaluation, upgrading, package revisions, and actually ended up taking multiple systems and doing complete overhauls from Linux over into Debian. I'm sorry, from HP Unix over into Debian Linux. We both have a passion for well executed, simple, easily extensible automation systems, and Sahoma has been a heavy adopter of Codesys and OOIP. Guys, we have project experience, proven experience using building in-house SCADA systems, building in-house web platforms. We have unconventional .NET Java developments. We've done blockchain and distributed secure by design data recording and ledgering. We've got machine learning tools that are out there right now that are helping our customers. Trainable vision systems have been put together, and agile process with continuous delivery models, right, is something that we're very big into. We've done purpose-built hardware and embedded system design. That's kind of our jam. And actually, we have our own weapons-grade compiler and tool chain for very low-level components and firmware that gives us some really, really tight security and deep understanding and test ability into component level criticality in your embedded system deliveries. Lastly, Sahoma Controlware is interested in contributing to the industry as a whole through things like this content and doing open source projects. We have several different things that are coming out. As a matter of fact, all the code that you'll find for this this tutorial that we're going to do is going to be available on our GitLab, which is available at gitlab.sahomascada.io, and I'll make sure you guys have links to all this stuff, and we'll talk about it a little bit more when we get into the actual tutorial. Anyway, thank you much. Again, thank you to Justin. Thank you to his family. So without further ado, let's hop over into screen share so that you can take a look at what it is that we're going to be starting to do. MEVB. Here we go. Okay, what do you need to do this task, this project? You need a Node-RED instance that's running anywhere that's accessible. That can be local on your laptop. It can be on a Opto22, a Wago PFC. It can be run on a Raspberry Pi. You just need to have a Node-RED instance that's running anywhere. If you want to run a Node-RED in the cloud on a VPS, you can use an AWS instance, Google Cloud instance. Linode is one of my favorite. I've got a promo code here for you for November if you want to use that. It's $100 in free credit. DigitalOcean, if you want to use them, there's a free credit link here. Or SSD Nodes is really a fantastic VPS. They've got ridiculous prices on long-term nodes. 8 CPUs, 32 gigs of memory, 320 gigs of storage is like $9 per month if you pay for the whole year. So it's pretty fantastic. An MQTT broker that is reachable. So you can run both your Node-RED and your MQTT broker at either one of these locations, either on your Node-RED instance or in the cloud or wherever. Anywhere that it's reachable, I'd particularly like BurnMQ. It can be any broker, Mosquito, Hive, RabbitMQ. You can code your own. I've got a video on how to do that in Python. You can see my video on that. Database that you want to use for history. I'm going to use an InfluxDB and a timescale DB, which can also be substituted for a regular Postgres DB. Any DB from anywhere that that Node-RED can interact with. It can be running in the cloud. It can be running on a different VPS. It can be running local. It doesn't matter. Cassandra. You can use Mongo, Dynamo, any DB. You may also want to have an MQTT test tool, such as MQTT Explorer or MQTT-FX. MQTT-FX is the Eclipse project's tool. It's downloadable from them. On MQTT Explorer is in the App Store for Apple, Android, a few others. You might want to have a Grafana. Same rules. Run on the cloud, run on your machine, doesn't matter. It just needs to be reachable. If you want a way to install all of these because you don't have them, the Industrial IoT Stack project can do basically all of these with the exception of like an MQTT test tool. It was originally built based on Peter Scargill's the script for Raspberry Pi. I've got the newest one forked over on our Sahoma GitLab, and I'm currently crafting some scripts to add some different industrial stuff. So that's actually a good project to go ahead and fork or to clone and follow, because there'll be some new stuff coming out with that very shortly. You may want to have a way to access your system over the internet. You can add your own domain. If you want to use a Cloudflare account or either Linode or DigitalOcean or AWS, all have DNS servers. You can use a reverse proxy. That's going to be part of what's also available from the Industrial IoT Stack project via Nginx. And then we've got, Duck DNS if you want to use that, or a no IP kind of installation. Any way you want to do it. You're going to have to port forward, at a minimum, ports 80 and 443. You're probably also going to have to port forward 1883 for MQTT data, or 8883 if you're using SSL certificates. If you want to secure your Node-RED, there's a couple different ways to do that. I'll show you how to do it within Node-RED. Any other questions, just catch me on LinkedIn. You can catch me on the IoT Discord channel. Shout outs in here and other stuff like that. So other than that, let's get going. All right, now that you got your Node-RED up and your MQTT broker and everything going on, we can go ahead and hop right into a browser and head over to your Node-RED instance. What happened there? Just let it load. Alright, here we go. And this is going to be the flow that we're working with. This one and this one at the moment. This simulation flow. As I said, all this stuff should be available in the GitHub. And you should be able to just go ahead and import it right into your flow using the import dialog. Okay, so to kind of break this down for you and explain how it's working so that you can modify it for yourself and kind of move some things around, make it work for whatever your particular use case is. The way that we have this set up is these trigger nodes up here, these timestamps, do some small functions that we have written here, and then we have these iterable timers that are doing an interval at 55 seconds and 30 seconds each to interval some of these other functions here. All right, so if you're not familiar with Node-RED, the function node allows you to write JavaScript functions right into a blank node and create your own scripting. That's pretty much what I've done for virtually everything here. So to kind of explain, where we need to start is right here off the bat anyway. And so the first thing we're going to do is put a good bit of comments in here. I'm going to add some more into each one of the scripts as we kind of go through them. Essentially, the first thing we're going to do is we're going to set a start time when we trigger our inject node, and then we're going to flow.set the sim run. The sim run is the simulation on-off bool. This kind of keys everything to either operate or not. Without this guy being on, basically nothing's gonna transmit or send, or it's just gonna sit here doing nothing. Then we got some initial values for some variables that we're gonna set, and we're just setting some different variables. Nothing too important. These are temperatures for pump 1 inlet, pump 1 outlet, pump 1 oil. We have a tank 1 level and a tank 2 level that we're setting. And then these other undefined variables are basically being set. They're creating the name, but we're just not setting any kind of a value into it. We'll do that in some of the scripts down here. But all of these variables are basically in the flow context. The flow.set is storing a variable into the flow context. The flow context is available to all the different nodes in the flow. And you also have a global context, which can be used from flow to flow between one another. We use mostly the flow context with this, but global works just fine as well. We also have a subset of this, the simulation stop, where when this inject node triggers, all it really does is set a stop time and then just sets the sim run bit to false. And if you do end up triggering any alarms, which is not something I'm using right now, but it's definitely something I'm planning to build some functionality out to support. Any of your high or low alarms, when they're triggered, this will reset them and put them all back to false so that they're not running high on you. All right. So that's kind of where you start. Next, these two inject nodes, the 55 second is only going to the level control, and the 30 second is going to our temperature measurement and all of our other nodes down here. Right. Once you've triggered these one time, they will iterate every 50 seconds or every 30 seconds, and inject into these functions. The level control function and the temperature measurement function are really the only two that are actually doing any kind of a manipulation of data. All the rest of these are just set points and then doing some alarming and stuff like that. It's pretty simple. So in order to walk through this, I will show you guys this, and you should be able to basically take a step back, use it on your own, and modify it for whatever it is that you need. So imagine that we have two tanks, two pumps, and each of those has set points and alarms associated with them. The pump stays off until the tank reaches a certain level, and then it kicks on and drains the tank. Once the tank has reached a low level, a stop level, the pump shuts off, and incoming fluid flow then fills the tank back up to keep the cycle going. Okay, so for our level control with that kind of principle where the pump drains the tank, we have some variables that we set up. They're pretty simple. Level 1, level 2, which is for tank level 1, tank level 2, pump 1 run, pump 2 run, which is our pumps. And then we have this PSS, which is a pump start stop. Then we have some parameters that we set for high and low values. And that will get used to create our random operations. Okay, so pretty simply, let me segment these off a little bit better for you. Okay. First thing we're going to do is we make a function called random where we use our high and low parameters, and we do a return with a random math function into this variable called step. So we're creating a step that's just a random number between 0.001 and 0.009. Then we're going to go ahead and set that into our context. And then we're going to use the variable sim to tell us if we're actually running or not. So down here we got some if statements. If simulation is active and pump 1 is not running, then level 1 or tank level 1 is added to the step variable, which is a random small number. Then down here, if simulation is active and pump 1 is running, tank level 1 is subtracted by the step and the tank level is decremented. This the level 1 here is really the optimal thing you're looking at. This number level 1.2fix2 is just to try and, for the most part, pin a 2 decimal use onto the our numbers here. Trying to keep it to 2 decimals, it doesn't really work. You'll see in the database, we constantly get levels of, that have way more than just 2 decimal places, but I'm trying to find the best way to do that. But for right now, it mostly works. So essentially just level one, and then step. The number to fix is just a function to set the number of decimal places, right? So that's all this does. This just basically, if the pump is true, add our step to the level. If the pump is off, if the pump is off, add our step to the level. If the pump is running, then decrement, subtract the step from the level. And then we basically use this function down here to watch the level with the start stop set point and decide when the pump should be running or stopped. So your pump one run, true false, is set by these two if statements, which are essentially comparing a level one greater than or less than to pump start stop level set points. And then we do the same thing here, where we call step and get a random step level, and do the same thing over again for tank level number 2. That's it. And then if down here at the bottom, if the simulation is true, then we set the message payload to a JavaScript object where tank level is equal to level 1, tank 2 level is equal to level 2, pump 1 run, and pump 2, and all of our values get wrapped into here. Then we do a context set for our tank levels and return a message. That's it. So here, I will do my best to show you guys. Let me see. Kill that one. Strap it to that one. And essentially, let me just turn this off for right now. Stop everything. Let's delete all of our debugs. Go ahead and start. And when we trigger at 55 second, it sends a timestamp to here. And what we're looking at is our JavaScript object. We have a topic of Sahoma MQTT Gen level pump status, and a JavaScript object with tank 1 level, tank 2 level, pump 1 run, pump 2 run. And then that gets sent over MQTT to here. And you should be able to see the same thing. Yeah, here it is. I think we're actually looking at the incoming message. Let's take a look here. So we're going to do it again. Let's deploy it. There it is. So this is coming from this debug. And if we switch over to our database tab where we have the MQTT in node, this is the latest one. And it's the same message, right? There we go. Now, adding these in, this is going to generate a bunch more traffic. So what we'll do is kind of look at the temperature measurement, which is the next one. And it's very, very similar to the level control. All we're doing is, here, let me turn this off. And then we'll stop these. take this. Find it in the list. There it is. Deploy that. Start. Generate. Stop for a second. Okay, let's take a look. So, doing our temperature measurement, you can see we got a temperature, out temperature, an oil temperature, an in temperature, an out temperature, and an oil temperature for each of our pumps. So, when we look at this, again, we get some variables, and we get our pump run status right from the flow context, which was set for us in this function right here. The flow.set pump 1 run false, or pump 1 run true, or pump 2 run and pump 2 run here. That's these context variables, which we are getting and setting to our local variable here. Then we set some in temperature minimum and maximums. And we have our random function here with our high-low. We do another step and we check our simulation. If the sim is true, pump 1 run is true, and the temperature's pump 1 in temp is less than the in temp maximum that we're going to do in addition. If it's greater than the in temp minimum, we're going to do a subtraction. This work is right. Yeah. If it's less than the max, greater than the min. Then we're going to set our temperature pump 1 inlet, temperature pump 1 outlet, temperature pump 1 oil. All the same way. Based just solely off of whether the pump is running or not. If the pump is running, we're going to go ahead and increase our temperature until we hit the max, or we shift back into pump run being false. Then we start decrementing. That's it. That's all. It's just each iteration we do a step in order to get a random value by which we're going to increase or decrease. This gives some kind of staggered movement. Instead of having real even looking curves up and down, this makes it kind of jump around a little bit more than just on a real scheduled kind of a pattern. Gives it a little bit more of a real world feel. And then we set message payload to the temperatures. And we set the topic to our MQTT gen and return a message. And that's where we get this. And if we look here, that's basically what we saw come in here with our temperatures coming in. All right. Very simple. Our set points is much simpler function because literally all we're doing is setting some hard-coded functions. These can easily be changed just by making a quick change here. Hit done and deploy. Then these two JavaScript objects here, PSP, ASP, which is pump set points and alarm set points, right, are then handled into the context data and set as a payload and transmitted over MQTT. Now it gets interesting because now we're going to take that alarm data, which we just set with those set points, and we're going to go ahead and grab that out of our context data here for our alarm set points here. I think, let me get everything back to setup. Yeah. And that one. That one. Okay. Done. There we go. And then we're going to, okay, cool, everything's going there. Deploy that. Go ahead and start our simulation and get these guys going. And then we set these alarm set points with this set points function. These values here. And then we're going to our level alarms function here. And we're going to get the alarms. Then we have this variable called tank in alarm, which is literally like which tank is alarming. And a few other variables, which are your levels, the alarm set points, your alarm object, and simulation. And then we're going to check the simulation. And if level 1 or level 2 is greater than the set point for tank high set point, then we're going to do a little subflow here, or a little sub comparison here, where if it's a level 1 alarm, then we set the tank in alarm tank 1, and if it's level 2, then we set tank in alarm tank 2 to be true, versus each one of these. And notice how there's no set them to false. It's because these, if they end up going true, you have to do your reset in order to flip them back. But for each one of the levels, alarm high, alarm high, alarm low, low, all we're doing is comparing both level 1 and level 2 at the same time, and then determining if it's level 1, if one of these is high or low, if the condition exists, which tank is it in particular that the condition exists on. Then we set our payload solely to set point, right? That's the only thing we're setting here, is to the set points and transmitting. Because here we actually transmit the pump set points, which is your pump start stop. Your alarm set points just get created. So then we're going to set our alarm set points here. Transmit those. This function does nothing but then get the alarms themselves, which is these true false alarm, and set those into a message. And then we have our tank iteration, which is get the tank in alarm, set that into a message, and transmit it. Because you can't transmit more than one, you can't return more than one message at a time, not with a payload. You could set all these to different variables in a message, but that is actually more difficult when we look at doing our databasing. So essentially, we have these two, the level control and temperature measurement, where we just have some if statements. They essentially set the pump run to true or false based on the level, and increase the level or decrease the level whether the pump is running. Same thing with our temperature measurement, where we're just adding or subtracting based on whether or not the pump is running for several variables. And we're using a random generated step, a randomly generated value in order to give us an offset that's not predictable and a little more real world. Then we have all our set points and our alarming. That's all being handled here. And then once that's you've got all that transmitted, you start getting some bunch of MQTT messages coming through your buffer here. Then you can use your MQTT-FX tool on your laptop. You're going to want to set up your profile here with your connection settings. Then when you connect, you can do this topic scanner. And any topics that are they're being generated and sent to that broker that you're connected to will show up here. And notice we're looking for anything Sahoma MQTT Gen. We just grab these. By double clicking on them, we're going to add them to our subscribe list. Then we come over here. If we want to speed things along, we can just hit these triggers a couple times and see that our messages are being observed right in our broker, which is, again, if you use VernMQ, we can go to the broker. We can look at this little dashboard. You can't do a whole lot, but it will tell you how many messages it's queued, how many clients are online, if you have it clustered, if there's cluster size, and give you a little data about the broker. So that's pretty much it, other than to set up our databasing and format the data to go into a database, which we will tackle in another video. If you got any questions, let me know. Reach out to me on LinkedIn, put an issue in on the GitHub page or the GitLab page, and I will be happy to help out in any way I can. Alright guys, thanks a lot.